free energy. Not free, but it sure describes if something's going to be natural or not and just happen. And all these things that just happen naturally, you have to actually do work to stop them. Boiling point elevation, freezing point depression, complicated things like gene transcription or weather, right? Entropy also has a lot to do with it. So let's see if we can get some insights into entropy, just taking a look at stretching. So I don't have a bunch of rubber bands, but I do have these gloves, okay? And hopefully you grabbed one. So let's apply our Gibbs free energy equation, delta G. Whoop. All right. Apply our delta G equation to this. So the reaction or the process we're interested in is having a rubber band stretched and then it contracts, right? So let's take a look at this. Number one. Oh, where are all my quizzes? Oh, Monica, just pick on you. Delta G for this process. Now again, what's the process? Stretched. No, it's not stretched. Delta G would be what for that process? Positive, negative, or zero? Man, I hear all three answers. What you have to ask yourself is, what's the big deal with delta G in the first place? Yeah, it's free energy, but it indicates spontaneity. How? If it's negative. So you ask yourself, is that spontaneous? This process. It starts here, ends up there. Is that spontaneous? Is that a spontaneous process? Start here, end up there. Can't stop it, right? You'd have to do work to stop it. Caroline would have to run up here, grab the thing, and pull that way with some force, right? So it's a spontaneous process. That's natural. So delta G would be negative. Yeah, but you had no idea why. Okay. After stretching a rubber band, Jasmine. After stretching a rubber band, it feels, okay, so you have to stretch it. Yeah, you sure you felt it, right? It feels warm, right? So stretching a rubber band, Alyssa, must be, right? It's getting hot, so that's exothermic, giving off heat, right? And the contraction. So Albert, stretching a rubber band is exothermic. So contraction of a rubber band must be endothermic. Yeah, absorb heat. Actually gets colder. So contraction of a rubber band must be endothermic. So then delta H, Victoria, for a contracting rubber band must be positive, yeah, because we said it was endothermic, right? Therefore, delta S must be, the sign for delta S. Remember, delta S is that funky thing that has to do with an abstract kind of idea. What would be the answer for this? He says positive, but he's just guessing, right? How are you going to figure it out? You have to play the game. Delta G is delta H minus what? T delta S. Okay. So, can T ever be negative? Can T ever be negative? No, because it's in what units? Kelvin. Like Celsius can be negative, Fahrenheit can be negative, but Kelvin never can. So T is always positive. Okay, the question is this delta S. Now, we said delta G is what for this process? And this process is a contracting rubber band. We said it was negative. And we said delta H for a contracting rubber band is positive. Okay. Now we're Miro. Whoop, I forgot my minus sign. Now you look at this. Delta S has to be what? Huh? Don't listen to these guys. Look at it. Right? Positive minus positive. Man, you can get 0 out of this. That doesn't look good. And you got to end up with something negative. Mario, what does delta S have to be? Right? You have a positive number minus a positive times x, and you got to end up with something negative. This number has to be big and positive, right? Because if it's negative, it's going to cancel out with that negative. You know that it's not going to work, right? So it didn't be positive or a positive if it was negative. So it needs to be positive and big. So the entropy is actually increasing when you let go of that rubber band. So at the molecular level, at the polymer level, you stretch it. This is what it looks like. There's this cross-linking that goes on in polymers. They're really long molecules. They're huge. Right? You stretch it, let it go, and then look how these little cross-linkings, this interaction's all over the place. Before it was, looking kind of nice. It almost looks like a ladder. So upon contraction of a rubber band, the energy in the rubber band becomes more, everybody, dispersed. Right? Because look at it now, it's all over the place. Before it was like a ladder. Boom, boom, boom. Okay. Interpretation of free energy. When delta G, Gibbs free energy for a process, is what, Vanessa? Is less than 0. We can do work. Exactly. It has to be natural. Because if it's not natural, how can you use it to do work? Oh, I mentioned this last time, Mari. I was ahead of myself. Remember I was pushing on the chalkboard or something like that? Trying to move the wall. A physicist defines work as what times what? Anyone remember? Force times distance. Pushing on the chalkboard, did I do any work? No. Force times distance. So that's probably more information than we need to know. But the point is it needs to be a natural process for you to use it to do work. Calculating a thermodynamic equilibrium constant. Man, we've had Kas, we've had Kbs, we've even had Kws and Kcs. But we've never had just a K before. Now we have just a K for the equilibrium constant. They're going to call it the thermodynamic equilibrium constant, so we can relate it to delta G. That's the whole point. In Kc expressions, going back to them though, when we wrote products over reactants, Kc expressions, Lauren, all the concentrations, it doesn't matter if it's a gas, a liquid, or a what. Right? Well, liquids don't show up, do they? Gases or aqueous. Everything was expressed in units of what? What units do we use to express concentration? Do you remember? Listen to Albert. Albert knows. Big M. Now, what is big M, though? Molarity, which is concentration, which is what over what? Yeah, big. Moles over liters. There you go. That's what big M was. Okay, but now in K expressions, concentrations are in units of, what do you think they're going to use? They're in concentrations. Now, what units do you have of concentration to pick from? You've got weight percent, you've got molality, you've got molarity, they're going to use molarity again. right? They can use the molarity again, except for what? Now, here's a hint. Whatever you pick, its units are in something to do with partial pressure. Gases. So gases. You see gases. You don't use concentration anymore. You use the partial pressure of that gas, and in what units? Someone said ATM, atmospheres. You have several to pick from. Atmospheres, millimeters of mercury, pascals, but atmospheres. Fine. You have to follow their convention, otherwise you can't use their numbers when you Google them and stuff. So, atmospheres has to be the units for the gas. Now, what is partial pressure? Do you remember? Ooh. PT equals, this is a good way to define, well, that's not partial pressure. PT is total pressure, but it's the sum of the partial pressures. So you could say big P, I don't know, what's all in this room? What gases? A lot of nitrogen, about 71% nitrogen. What else is in there? CO2. You'd be dead. I thought you'd name this one first. Oxygen. Anything else? Anything else? Not hydrogen. Hydrogen, if I let it out of a balloon, Earth's gravity is not strong enough to hold it. It just goes out into space, all the way up. Might take several days, but it's gone. Ooh, I bet you there's a lot of water vapor. That's a good one. Okay. Good. So if you add up all those individual pressures, dang, you'd have the total pressure in this room. All the partial pressures. How would you calculate any one of those? You'd use this law. What was this law called? The ideal gas law. And all you do is you pick one. Nitrogen. The partial pressure of nitrogen. This is our second partial pressure equation, was the ideal gas law. So you could calculate the partial pressure of nitrogen using the ideal gas law. You just had to remember what variables to put a subscript on. So you put it on the P for partial pressure. What other subscript did you put the N2 on? If you wanted to get the... Now T is temperature. Should all the gases in this room have the same temperature? Yeah, otherwise, one corner isn't colder than the other corner. So they all have the same temperature. So you don't put a subscript on the T. N. It was N, the number of moles, exactly. See, the number of moles of nitrogen you put into the equation. The volume of the room, gas constant R. Okay. So that might be more than you need, but in case you need it for the homework, you can calculate some partial pressures. Relation between standard Gibbs free energy and the thermodynamic equilibrium constant is below. So delta G0 is negative RT natural log of K. How do you get this delta G0 thing? Tables. Why do you say tables right off the bat? Because you see the little zero. You should put the arrow here. That means tables. Well, it really means what? That's the applicable idea, tables. But it means standard temperature and pressure. Right. One atmosphere and 25 degrees Celsius. But anyway, okay. How do you solve for K? Well, might as well just say what this stuff is first. So we get delta G0 from the tables. What about this R? Might as well answer this question. Which R do you use? I give you all these, but there's a gazillion. Well, not a gazillion. There's like 3 or 4 different R's. Oh, there's one. This is the one we use a lot. 0.821. Do you remember this? Liter atmospheres over moles Kelvin. But don't use that one. Because we need We need to have units of energy in there. We need to have joules. So we're not going to use that one. I don't know if we ever use this one. The units for it are joules per Kelvin mole. You want to know the number? There it is. Vanessa found it. 8.314. All right. Have a good weekend, Victoria. 8.314. That's the R you have to use. Okay? What's T in this equation? Temperature. And what units should it probably be in? Kelvin, because look at the R you have to use. It's got Kelvin in it. Okay. So before we mathematically solve for K, we got to put in all these numbers. Put in a number for delta G0, R, and T. If T is in Celsius, how do you get it into Kelvin? Add 273. Remember this. Good. Okay. Do you see the conflict before we start doing the math here? R is in what units for energy? Joules. Delta G is in what units for energy? Kilojoules. So convert one or the other. You're going to have to. Either convert the kilojoules to joules or the joules to kilojoules. Okay, so you do that. So you've got a number for all this stuff. A number, natural log of K. Okay. So what I would do is I would just divide this guy by these two, then do what? Take it to the e power. Remember doing that? So it would kind of look like this. I think that's the easiest way. You're going to have e to that number equals, I guess you could say e to the ln k, but they cancel out. That's how you get your k. Okay. And we'll do one of those. What is the difference between delta G and delta G0? Monica, what's the difference between delta G and delta G0? Delta G0 is the standard one. Delta G isn't. So you can't get delta G from the tables. Only delta G0 you can. So how can you get delta G? Now, the equation, right? And this little t down here probably means what? Temperature. Delta G at that temperature is, and then you calculate it. Okay. So where do you probably get these two? The tables. Why? Because you see what? You see the zeros, exactly. Tables. So you just got to plug in the temperature in what units probably? Kelvin. Have you seen the other trick to doing this? If you do the tables, you get kilojoules per mole. Right? Then we have the kelvins, whatever temperature that is. Then you have joules per Kelvin mole. All right, for the delta S. Did you see the problem in the homework from the last class? You had to, hopefully you converted, right? You converted those kilojoules to joules, or you converted the joules and the delta S to kilojoules. Otherwise, you could never get the answers in the back of the book. Okay, I say we're good to go. But let's make life a little bit faster. Let's just go to the boards and knock these out, and we can call it a day. So the hardest part about going to the boards is getting out of the seat, I do believe. After that, it's all fun. It's an attitude, Jasmine. It's an attitude. Give the expression for the thermodynamic equilibrium constant for the following reaction. So I'm giving you the reaction, and we just need the thermodynamic equilibrium constant expression. So what does that mean? Big K. And it's going to be what over what? Products over reactants. Exactly. Products over reactants. I think you need a little +2 though on the magnesium. You gotta have to have your charges in there. Oh, Lauren, look at what Albert's doing. Yeah. There you go. Oh man, he's on today. Do you remember? Okay, let's write this down so you guys remember this. Jasmine's got it. I think Ramiro's got it. Products over reactants. Magnesium. Hydroxide, but to what power? Second. All over nothing. 1. Because it's a solid. Right? It's a solidness, so you can't have solids and pure liquids. They don't show up in any K expression. So remember this? Okay, let's try 60 then. The thermodynamic equilibrium constant expression again, but for this reaction. There's a trick to it. Man, Ramiro knows the trick. He knows the trick. He must have read the book or something. Right? Because they're any gas, you can't use big M. If you're going to plug in a number, it has to be in what units? ATM. So that means if you write this expression, you can't use brackets because brackets means big M. You have to use P's and have a little subscript for the compound, for the chemical. And if it's squared, fine, square it. If it's cubes, fine, cube it. Okay? Make them subscripts so they can't be so big. Right? We're good? You agree? And everything has to be in atmospheres. All those pressures have to be in atmospheres. Okay? Let's check out 61. What is the standard free energy change at 25 for the following reaction? Get necessary information from Appendix C. Looks like Vanessa and I are the only ones who care to bring a book. All right, we got to find... Vanessa, help me out here. I need hydrogen gas. I'll find the HBr. Hydrogen. Maybe I got to look up bromine. I guess you have to look under bromine. And we are after delta G. Delta G is negative 53.5. Okay, this guy's negative 53.5. Our delta G numbers in kilojoules per mole. Okay, so for HBr, I found negative 53.5. And Vanessa, you found? They're both zeros. Oh, that's nice. Okay, so there's your values. You should be able to solve this. What's delta G0 for that reaction? And we gave you the delta G standard Gibbs free energies for everything. Remember how to do this? Yeah, it's products minus reactants. Exactly. And don't forget to multiply by the stoichiometric coefficients. What is this? Minus? You mean times?
Yeah,
So it'll be products, though, minus reactants. So it'll be 2 times this guy minus 0. So did you get like a negative 107 or so? Yeah, because it's products minus reactants. So a negative 107 kilojoules per mole. What is the value of the thermodynamic equilibrium constant? Okay. Now I give you all the equations. You might remember it already, but delta G is negative RT natural log of K. Oh, and I give you all the constants too, right? So I'll give you our constant. Right, these are all written on top of the quizzes and stuff. Or you have it, because you have the exam 4 equation sheet, so you should have all that stuff. They want to know what K is. So I suggest plugging in the numbers. It makes things easier. Right? And watch your units. Watch your units. Anyone not sure what to do? Let's see. You want to make everything into joules, right? I think there's 100 and... Let's see. You are going to joules. So in a kilojoule, there's 1,000 joules. So the kilojoules cancel. So you have to multiply by 1,000, not divide by 1,000. Right? If you want to go that route. But if you want to go kilojoules to joules, yeah, you need to multiply by 1,000. But if you want to go from joules to kilojoules, divide by 1,000. Right? So if you just want to pick one, like the 8.314, get them into kilojoules, you just say, okay, times 1,000 joules in a kilojoule, and you'd have them. You'd have him in, right? You'd have him in kilojoules. So that's one route to go. Thousand joules in a kilojoule, right? Mari, see, this is how I did it. I got my R into kilojoules. So if you write it out, then you can't screw up. The other thing you can do that's kind of easier, and you won't screw up doing it this way, is there's a negative 107 kilojoules per mole. Wherever there's a K means kilo. Just replace that K with times 10 to the third. So that's negative 107 times 10 to the third joules per mole. And that always works too.
Sounds easier.
So, yeah, that sounds a lot easier than remembering what to do and multiply stuff.
This?
Yeah, and then, so what I would do is I would divide this negative 107 by these two, get a number, and then raise it to the e power, right? Because you have to bring these over first.
If it's in kilojoules, you times it by 1,000 to take it 2 joules. Right?
Yeah. In fact, there's an easier way to do all this. We know it's negative 107 kilojoules per mole. Wherever you see the K, just replace, because that's kilo. Just replace it as times 10 to the third. No. That's times 10 to the third. Negative 107 times 10 to the third joules per mole. So you have to multiply it by 1,000 if you want to get it into joules. Right? So I think it's easier just to remember, oh, kilo times 10 to the third. Just put it in there. Then there's no memorizing.
So did I do this one wrong? Yeah, because you don't convert this.
She can do it that way because now this guy's in kilojoules. He's in kilojoules. He's in kilojoules. So this is the other way.
Okay.
So you can do it this way where everything's in joules, or do it this way, everything's in kilojoules. Because it works. Because regardless, we should all end up with the same number equals a natural log of K, no matter how you do it. So what?
Right? Because the R is negative R.
You have a negative on both sides here. So you have two negatives, so you can cancel them out. Yeah, the negatives are going to cancel out on you.
So put it to the E, does that?
Oh, I don't know. Let's see. You got 43.19?
Does that become negative?
No. Let's see what you guys get. Did anyone solve for a natural log? Natural log. Okay. Jasmine got about 44. Anybody else get about 44 for the natural log of K? No, it's fine. Well, 43.18, 43.2. So no matter how you do this, everyone needs to end up with the same intermediate step. Something like 43.2 equals a natural log of K. Negatives cancel out. You divided negative 107 by a negative 0.0. All right, negatives are gone. I just want to make sure everyone gets this far first. So make sure you can get 43.2 equals a natural log of K. Then you raise both sides to the what power? E. Okay. So we'll have E to the 43.2 has to equal E to the natural log of K. And these guys are just cancel out. What the heck? Wow, he stopped writing. He stopped writing for me. What did you get? E to the 43.2? It's 10 to the 18th. Yeah. Man, my pen just totally died on me. I don't know why. You should get a final answer is 5.7 times 10 to the 18th. Yeah, times 10 to the 18th. Boy, this would take forever if I did it this way. Right? Oh, that equals K. I got to write a K here. I can't even see it here.
Is it kJ over kilojoules over?
No, there's no units for K. Equilibrium constants, no units. Okay? So. that's about it. I mean, so just when you're doing the homework, make sure you watch your units, and you'll do fine. Come by if you have some questions. I'll be glad to help you out.